Okay, this video is on formation reactions and then using formation reactions as the third way to calculate delta H or enthalpy for a reaction. Okay, so the background information before we get into formation reactions is that enthalpy or heat for a reaction, the change during that reaction depends actually upon the conditions in which the reaction is occurring. So for that matter, we can end up with different delta H values if reaction conditions are different. So in an attempt to standardize that discussion, scientists picked what we call a standard state, and it has to do with a temperature and a pressure for reactions. So they picked a standard pressure of 1 atmosphere, and even though we're not super familiar with pressures yet, 1 atmosphere is the pressure at sea level, so relatively standard across the board for a reaction to occur. And then the second one is the temperature, and they picked 25 degrees Celsius, which might seem like a strange number, but 25 degrees Celsius is approximately room temperature. Most reactions that you do in a chemistry lab occur at room temperature, and that's why they picked 25. So this kind of standardizes our reactions so that if we're talking about a reaction that we did on Monday versus a reaction we talked about that we did on Friday, but they both probably occurred at pretty much standard conditions. And so therefore we can compare their delta H's. So that brings us to standard heat of formation, okay, which is the heat or energy change for a formation reaction. And so your next question should be, what's a formation reaction? Okay, so a formation reaction is a specific reaction that is specific to the study of thermochem. And formation reactions are happen or occur when 1 mole of a substance is formed from its elements in their standard state. Two keywords being the 1 mole and elements. So if we think about, and you don't have a lot of room here if you're on my note packet, so if you would like to go to the back of the note packet or an extra sheet of paper or something to do a couple examples, that would be helpful. Okay, so an example would be the formation of H2O, okay, water. And so if we're going to write a formation reaction for water, it needs to form H2O from its elements, not its ions, which is where students get confused. So the elements that make up water are hydrogen and oxygen, and we have to think about how do they exist in their standard state. Well, hydrogen exists as H2, diatomic and a gas, and oxygen also exists as O2, which is a diatomic and a gas. So this is the two elements, hydrogen and oxygen, that make up water in their standard states. Now I have to balance this just like anything else. And so when I go to balance it, this is my reaction. Now, as written, this reaction does not meet the criteria of the definition for a formation reaction. Okay, so this is actually not formation. And the reason why is that formation says 1 mole of my substance, and I have made 2 moles. So we can get it to formation by dividing everything by 2. And that's where you might say, oh, that's why sometimes there's a fraction like 1/2. And now because I form 1 mole of H2O from its reactants in their standard state, this is a formation reaction. Okay, so formation reactions can be a little bit tricky because students a lot of times want to try to form it from its ions, right? That's not what we're talking about. So let's do 2 examples. Again, if you don't have room, just go to the back. Let's do the formation of magnesium hydroxide. And then in a separate example, the formation of calcium carbonate. So if you would like, you might want to pause this video and attempt to do these on your own. But of course, you can just listen to my explanation as well. Okay, so the formation of magnesium hydroxide, well, that would be my product is MgOH2 solid. And the elements that make up magnesium hydroxide, well, there are three: magnesium, oxygen, and hydrogen, and all we have to do is think about what their standard states are. Magnesium is a solid, right, and not a diatomic. Oxygen is a diatomic, and it's a gas. And hydrogen is a diatomic and also a gas. So there's the elements in their standard state making magnesium hydroxide. It is already balanced. We do in fact form 1 mole of my product. So this is the formation reaction for magnesium hydroxide. The calcium carbonate, we do in a very similar manner by saying what are the elements that make up calcium carbonate, and calcium, carbon, and oxygen. And all we have to do again is think about what are their standard states. So calcium is a solid, carbon is a solid, and oxygen, of course, is a diatomic as a gas. I need to balance this reaction, and so if I balance this like we normally balance, the O's causing the problem. I need 2 here, 3 here, and then 2 and 2. However, I cannot leave this reaction like this if I'm attempting to make a formation reaction, and that reason again is because I have formed 2 moles of calcium carbonate. So to get it to formation, I divide everything by 2. That's where that 3/2 comes in. And that is my formation reaction for calcium carbonate. Now, why are formation reactions important? So they're important because we now have this table, right? This stapled table of all of these numbers called thermodynamic quantities for selected substances at 298 Kelvin or 25 Celsius. I don't have that image inserted in this video, but you should have that. You should have that reference sheet with you. And we have the values along with a couple other values in this table, but the value we're looking for and are concerned with is the delta H of formation. And so pretty much for many numerous substances, there are the delta H of formation values in this chart. So for example, this last reaction we wrote, the formation of calcium carbonate, if I go into that chart and I look up calcium carbonate, we find that its delta H of formation at standard conditions is negative 1207.1 kilojoules per mole. And so what that means is that the formation of calcium carbonate, the formation of 1 mole, right, of calcium carbonate, releases 1207 kilojoules of energy. So this is an exothermic reaction. So for any formation reaction, I can go directly to the table and I can look up the value of delta H of formation. Okay, you'll find if you run through the chart that there are lots of zeros, okay, for delta H's of formation, and those correspond to elements or diatomics who are already in their standard state. So if you think about that, the delta H of formation of 0 makes sense. This is the energy released or absorbed when a substance is formed. Well, your elements and your diatomics aren't formed, they already exist. And so there is no formation reaction occurring for an element or a diatomic, and so there is no delta H of formation. So all those zeros you see in the chart are for elements and diatomics in their standard state. Okay, so moving on. Now, how does this help us? Okay, so you have a bullet point on your page that says something along the lines of, for a reaction that occurs at standard conditions, you can calculate delta H for that reaction using this formula. Okay, and this formula looks quite confusing, but it's really not. It's actually quite a simple formula. So it says that delta H for any reaction can be found, and this Greek letter is sigma, and it means sum. Okay, so addition. So it says if we take the sum, if we add the delta H's of formations of all of my products in a reaction, and I subtract from that, again, the sum of all the delta H's of formation of my reactants, I will end up with delta H for the reaction. For any reaction, I can do this, as long as I have a chart with delta H's of formation. So I refer to this formula as P minus R, products minus reactants. That's how you'll hear me talk about it in class. But this is the third way to find delta H for any reaction. So I'll do an example. And my example is calculate delta H for a reaction, or for the reaction of CO gas with CO2 gas to form a CO2. Okay, so before we do anything, we need to write a reaction. So my reactants are CO and O2, making CO2. Of course, I have to balance this reaction before I can do any delta H calculation. Okay, so 2, 1, 2. And of course, my goal is what's delta H for this reaction. Obviously, I can't use Q equals MC delta T. I don't have any information, and this is obviously not a Hess's law problem because I also don't have reactions that I can manipulate. So this must be this third way to find delta H, which is what I call P minus R. Okay, so here's how it works. So first we think about my product, right? In this case, I only have one. I have one product, and it's CO2, gas. So I go to my chart, my reference page, I find CO2. This is the hardest part, finding the things in the chart. I find CO2 listed under carbon. I find it as a gas, making sure I'm reading the right number, and its enthalpy of formation is negative 393.5 kilojoules per mole. Okay, and that's the delta H of formation for CO2. Now, this is the only tricky part you have to pay attention to. That value is for 1 mole of CO2. I don't have 1 mole. I have 2. So I'm going to have to double this value by multiplying by 2. Essentially, I'm multiplying by 2 moles. My moles cancel, and that's going to leave me with kilojoules as my final answer. But I'm not done. That's just my product, right? I've only taken care of my product here. So now I have to take care of my reactants. So P minus R, so my product, I'll do this math all at the end, minus my reactants. So again, I have 2 COs. I'm just going to go ahead and write the fact I know I'm going to have to multiply that value by 2. I look up CO gas in my chart. It's negative 110.5 kilojoules per mole. Right, essentially, my moles cancel. And I'm going to add to that the enthalpy, remember, sum of my reactants. And so the enthalpy of formation of O2, you might have to look this one up, but if you remember what we just said, the enthalpy of formation of O2 is 0. So actually that's not going to change anything mathematically. And now I'm just careful with my calculator in how I input my numbers, making sure I don't miss my signs and making sure I don't forget that this is a subtraction. When I do the math, I end up with delta H of negative 566 kilojoules. This is an exothermic reaction, and that is delta H for this reaction. So essentially, as long as you have a balanced equation and you have this chart of your delta H's of formation, you can use what I call P minus R to find delta H for any reaction. There's a couple practice problems on the back of this packet. You're welcome to try them. I would to see if you can